Today we have a great speaker, Rob Sherwood. Probably everyone knows his name if you are working in SDN, network virtualization. He did his PhD from University of Maryland College Park, and he did the first prototype for OpenFlow-based FlowVisor. So Rob is one person who has seen SDN evolve from academia to industry ever since it started. Today it's a great honor to have him here and hear his thoughts on how SDN is helping the bare metal switch adoption. So I'll hand it over to Rob.
All right. Thank you. All right, so thank you very much for having me today. Yes, I'm Rob Sherwood. I'm not really old. I think that's what he was implying. So today I'm going to talk about a whole bunch of things. I'm going to talk about, and I think these slides will be available online. You people are welcome to take pictures anyways. They're not that great slides. So I'm going to talk a little bit about some of the motivation of how I see SDN being useful. I'm going to contrast what I'm going to call modern SDN with what I think most people kind of understand to be SDN, or certainly what SDN was back when I was at Stanford. I'm going to talk a little bit about some of Big Switch's technologies, some of the things that we're doing, more at a technology level and less on a product level. And then, in case any people think this is interesting, I actually have a fair bit of open source that we work on, and so there's even stuff that you can grab and play with if that's of interest to you. So the other thing is I do much better with interactive audiences, so if I say something that's ridiculous, or you'd like to make fun of me, or you just have a question, just raise your hand, I'll call on you. I'm happy to drop stuff. We've already got a joker. All right, so motivation. So how many people have heard of this company? No, seriously though, right? So everybody that I talk to at a customer level, and a lot of our customers are kind of high-end enterprise, they're asking themselves, how do I become more like Google? How do I get the cost savings that Google has, the economic efficiencies that Google has, the agility that Google has? And it's not just Google. Google's definitely got some special sauce, but Amazon's got some of their special sauce, Facebook's got some special sauce. All these hyperscale guys have figured out how to do networking and infrastructure and all these things in a better way than the rest of us. And so part of that's because they have a lot more money, and they can hire a lot more engineers. But the question is, are there things that we can learn from them that we can actually adopt and integrate, that I can turn into a product to sell to someone, or that you guys can take back to your own networks? And so what do these guys do? So we know what they don't do. They don't buy these large vertically integrated kind of standard off-the-shelf boxes. What they do is they write their own software. Depending on what flavor of SDN you want to talk about, it's SDN software. There's some sort of remote control. And they build it on top of what I'm going to call a bare metal switch. That is a switch where they can actually buy the box independent of the software. That's what these guys do. And you may have heard of projects like their Andromeda that they talked about at the recent ONS. They've also had, this is in the data center with their cloud work. They also have some wide area networking work that they do. But these are all largely SDN-ish type things. And so, okay, what does Big Switch do? Big Switch builds SDN software, just the software. We don't build any hardware. Maybe it was a bad decision to call the company Big Switch. We don't sell hardware, but we don't. We just sell the software. And we run it on bare metal switches. That is, switches where we get just the hardware and put the software on it ourselves. And we do use it to monitor networks and to build fabrics. This is the only product pitch slide that we have. I'll talk about technology for the rest of the evening, but I just want people to walk away. If you know nothing about Big Switch, this is the only slide that you really need to know and understand. So, as Vikram said, I've been involved with SDN since the very beginning, and at least in my mind, SDN has actually evolved a fair bit. And so, a long time ago, in a land far, far away, up in Palo Alto, in 2008, SDN looked a lot like this, or at least the vision how we thought SDN would work. And so, starting from the bottom, the belief was that a traditional networking vendor would continue to sell you the box, the whole box and everything that goes into the box, including the software, and they would have OpenFlow enabled as a feature on the side of that box. And then you would get an SDN controller, much like you'd get an operating system from somebody, and then that would have a fairly standardized API that talk to an SDN application on top of that. And you might get that from somebody else. And then you might have some automation tools that call into the application to provide policy on the fly or something like that. And this was the vision that we had for how SDN would evolve. this vision hasn't happened, and there's actually a lot of good economic and technical reasons for that. The vision that is evolving now, at least for the short term, and we will have to see how long this persists, is the idea is you actually get the hardware, but not the operating system. The operating system might actually come from someone else. Yes?
One quick question. Are you going to share the slides today?
Yes, let's share the slides. So the idea is you would get the operating system on the switch from someone else. You would actually have the ability to swap the software as you wanted on the switch. So how many people were here for JR's talk, a couple of months ago? Right, so JR showed you how you can do this. This is actually using those same mechanisms. And then the idea is that northbound API, that interface between the controller and the application, that is just a mess. Like, technically speaking, trying to get everybody to agree on what the OS level interface should be, I keep telling people it hasn't happened in the PC world. There is not a common API across Linux, Windows, and Mac OS. Why do we think that the switch vendors of the world are going to get together and build this? And more to the point, we don't even need it, right? So right now, what at least my company is doing, and a lot of other companies that I'm seeing, are actually selling those two components, the app and the controller, as one integrated solution. You don't have, and the idea is that most customers actually don't have internal development teams, or if they do, they're not going to waste them on infrastructure. They're using them to build things, to build money for their own company, build products that make money for their own companies. There's not a programmer at like a large Fortune 500 company that's going to build a custom application on top of a controller. They actually want just a discrete solution that they buy as a whole. And so the idea is you would actually get probably the network operating system and the solution, the app and the controller, all together as one package. You get it from one single source. And then the automation tool, the thing that actually hooks into the end customer's business logic, the OSS BSS integration, if any telco people here, apologies if I'm scaring anyone, that would then hook into the customers. And so what the customer sees is a little bit of scripting from their automation tools, the scripting that they already do internally. This is the model of SDN that, at least for the next bunch of years, I think is much more viable, and certainly what my company is doing. Questions?
So then why the distinction between an SDN app and a controller? Why not just a single thing?
So, so the question is, why distinguish between an app and a controller if it's one blob? So the answer is basically historical, although for what it's worth, internal to, for example, at least my company, there's an engineering distinction. So when we sell different applications, there's actually a huge chunk of code reuse. So the code is factored differently, even though that's not a customer-facing different solution. Does that make sense?
Yeah, I mean, for a customer, ultimately you're saying, it doesn't matter whether it's a controller or application, it's just a single thing, and they see a single thing.
Exactly. I mean, it's much like, God, I hate to go to the appliance model because that's not my favorite subject, but people like the appliance model that you buy for firewalls or load balancers and whatnot because you get an integrated solution. And the fact that one version of their products and another version of products might share code is a pure engineering efficiency point, not something that's relevant for end-facing customers. Another question behind you?
Well, isn't it clear, because an SDN app and an SDN controller can actually be two separate pieces?
So, absolutely, that is technically possible. What at least I have spent a lot of blood, sweat, and tears on is trying to make that happen. And the end result of that is you have that API between the controller and the app gets frozen in time, and then you have for every API that for every application that Big Switch has come up with, and we only have 2 that are public, and there are a bunch that are not, we've had to substantially change that interface. We have not come anywhere near to, at least even internally, settling on that interface. And so, it is useful to think of this model, but at least if your job is to provide end value to a customer, where they're not producing code in the middle there, because I'm not going to sell this software to Google or Facebook because they have more engineers than I do on staff, right? That might be useful to someone like them. The vast majority of the world wants an integrated solution.
So how about the open source controllers like Daylight and all? Do they come with the app or? So
the question is, what about the open source controllers? Those are great building blocks to build a complete integrated solution. And I absolutely believe those are the right things and will eventually evolve towards this model. The question is, how long will it take them to settle on a platform that can support a large swath of applications? And in the meantime, with this model, I can provide end value to the customer right now. And so those are absolutely the right thing. And in fact, a lot of what we build inside of here was based off of Floodlight, although it has evolved a little bit since then. So imagine at least if you were going to start an SDN company in the next 3 or 4 years, trying to say I'm going to build a better base platform and other people are going to build applications on top, I actually don't think that's a viable model. Now, starting with a third-party open source project as the base of your controller and then moving that code into there, I think that makes a lot of sense. Does this make sense, what I'm saying?
So I have another question. So if do you have like apps, like modular apps, so like, your customers, say, can choose a firewall and a load balancer and like say, certain flavor of routing separately as like different modules?
So the question is, and I'm repeating it because I'm on mic and all this stuff. So the question was, does Big Switch have modular apps like a firewall or a load balancer that we can swap around? The answer is not. So our applications are actually all in the control plane. So we have a monitoring fabric. We have a multi-tenancy data center fabric. Those are not swappable by the customer. The fact that they have a lot of common code is not a customer-facing thing. So you buy one product or you buy the other.
So the customer buy a whole solution.
They buy the whole solution. And I absolutely believe that 5, 10 years down the road, this left side model will become viable again, which is to say, as the APIs for the controller solidify, as we start to get enough experience building these things out, as the open source projects catch up to the state of the art of where the commercial is, I absolutely believe this is the eventual future. But in the meantime, so think of it in the early days of operating systems. The notion of an operating system decoupled from an application didn't exist, right? You had these purpose-built operating systems where the application and the operating system were very tightly integrated. And it really takes a mature ecosystem to get back to this. And it's something that's an interesting lesson, at least for myself. Just because you know where the road is going to lead doesn't mean you can skip down to that path. Like you actually have to go through every process in the road. And my claim, and at least what we're seeing right now, is that this is the phase of the road that we're on, even if this is where we end up in the future.
Is this northbound API also proprietary?
So, define proprietary. So, it is open, meaning that we publish the specs to it and we allow customers to integrate with it arbitrarily. At the same time, we don't bring that API to any standards bodies, at least anytime soon, mostly because we're trying to stay agile and keep up with the customer demands and the feature velocity. Does that answer your question? All right. I actually have a whole bunch more slides. So,
the SDN OS, who developed it? You developed it?
The SDN OS, yes, we developed it. In fact, a lot of the open source is on the SDN OS side, and I'll talk about that a fair bit on the switch side. Just a quick point about open networking. You guys will hear me say the word open networking, and I actually lose some people with that term. So if you think about kind of the aggregate throughput of a device versus how open it is, so is the hardware publicly available? Can you get at least a binary SDK for the packet forwarding? Is the device completely closed, but maybe there's some APIs to control the control plane, like maybe there's SNMP or maybe you have OpenFlow, versus it's completely closed, but there's only the SMP like interface MIBs or something that you can access. There's kind of this sliding scale of open, and it actually tends to anti-correlate with how fast the box is. So the biggest, fastest boxes that you can buy are the most closed ones. And the things that are the slowest, the most programmable, you can do anything with an x86, are actually the slowest. And so really what this movement is, at least in the short term, is about doing this, which is moving the 1U data center stuff, the leaves and spines, and the boxes that you can build out of it, a little bit more open. So at the end of the day, and I'll talk about this, the people who build the chips are still not publishing the hardware details. So you still can't build this entire thing up from scratch yourself unless you're under NDA with one of these companies. But it's definitely more open than it was before in a fairly real and dramatic way. So you can swap operating systems. You can actually load processes on the box. You can develop on these boxes. And that's a lot different from further down this spectrum.
So when you say open, so what do you like? Do you publish the source?
So I mean exactly what I have here, but let me get back to the open source. So the operating system on our switch, we actually publish all the source that we can publish, and I'll talk about that in detail. This is what I call modern SDN, and so this is really to level set versus what I think a lot of people understand how SDN and OpenFlow work. How many people think that SDN can't scale because of the way the flows are set up? All right, you guys are incredibly well educated because the vast majority of the world believes that. And so let me try to convince you why you should continue believing what you believe, that it can scale, and it actually is a very reasonable way to build a network. So what is a fabric? And so a fabric is honestly probably a marketing term at some level, but if you think about, when I think fabric, I usually translate it with my engineering hat onto a crossbar switch, something where you have a scheduler that gets bandwidth between point A and point B, and you can actually, there's no topology hangups, everything is as well connected to everything else. And you can even do nice things like you can say, a packet from 3 will get duplicated to go to 4 and 6, and you kind of arbitrarily broadcast within a piece of silicon. That's what I think of as a fabric. And it's not necessarily just a piece of hardware, it's also a useful software or network building abstraction to think of things like that. So how would you build something like this? So traditionally, something like a chassis-based fabric is what people would use. You would have line cards, you'd have a very fast fabric backplane that the line cards would plug into, and you've got a couple supervisor modules, things that are more programmable, things that run standard operating systems. That's one way of building a fabric. So another way of building a fabric, which is actually almost identical to this, is what I call a leaf-spine fabric. So instead of line cards, we have 1U leaf switches. Instead of a large integrated backplane, we have a collection of spines that serve that same role. And then instead of supervisor cards, we have controllers. And then the only difference between these things is the communication protocol between the supervisor cards and the line cards. There is a protocol that the supervisor says, oh, I found out of a new route, I'm going to insert that route in. That's a proprietary closed protocol that I'll jokingly call closed flow. And what runs over here is OpenFlow. It's a standardized mechanism for the controller saying to the individual components here are the forwarding rules that I want you to have. And so the reason why I bring this up is anytime that someone says SDN can't do X or OpenFlow can't do Y, I like them to come back to this picture because I try to tell them this is how our networks work today. It's not that there's one controller that controls everything. It's not that there's magic here that can't happen. It's just, we took a big sheet metal box and we blew it up. And in fact, if you look at the implementations of these big sheet metal boxes, they even have dedicated in-band Ethernet, and they actually even speak standard protocols like UDP and TCP over them. So depending on where you're coming from, this is either earth-shattering or really boring. Showing hands for earth-shattering? We got one. Really boring? All right, most of you are asleep. All right. So I'm starting, this is a funny new campaign for me. I'm starting WWCFD, what would closed flow do? Anytime you want to ask, for the rest of the talk, how does this work? How is this possible? I don't believe you. Ask yourself, what would closed flow do? Does this work with closed flow? And the answer is probably yes. And the answer is that the SDN-based products probably work pretty much the same way, because that's what the underlying hardware was built to do. Now, the question is, if it's just the same as closed flow, why would you still use it? Why would you do something different? And the answer is this even really the right question to ask? So we were talking about, earlier, just before the talk started, in terms of an Internet of Things, which is, let's make sure that all devices on the network have some sort of remote programmable thing that you can manage it remotely. That's really what SDN is about. SDN is about having a way to remotely manage a box in a standardized way. It's not necessarily about flow control or anything like that. In fact, OpenFlow, one of the biggest mistakes was naming it OpenFlow, because people think that it's flow-based because of that. And, and I'm to blame. Some of the early slides actually showed flow-based examples, which you can do with OpenFlow. But it ends up being hard to scale that type of solution, and I'll get into that in a bit. But I like to think of SDN. SDN is not a solution onto itself. It's a programming paradigm. You could think of it like object-oriented programming. It's a best practice. It's something that makes your design easier, but it's not something that in and of itself provides value to most end customers. Like if you're Google or Facebook and you've got an army of programmers, then sure, SDN is a solution in and of itself to you. But for most people, SDN is the thing that enables the actual solution to you. Questions about this?
I get what you're saying, but that's in line with the original model of OpenFlow, where you would allow the flow box with a standard interface to be managed better.
Yes.
What prompted the change? I mean, why not follow up on that?
Let me hold off. Let me give you a short answer now, and I'll give you a better answer when I get to more slides. But the short story was the people who were trying to provide the closed box just with the OpenFlow feature didn't want to throw out all of their software. They wanted to cordon off OpenFlow to a very small fraction of the total hardware capabilities. Because it turns out, that's most of the slide, but the punchline is the economic incentives are backwards, which is you're asking me, the switch vendor, to spend a non-trivial amount of time to build up an agent so you can commoditize me and throw away all the software that I spent a lot of time working on. And so not only is that a hard thing to do from an engineering perspective, the incentives are economically backwards. And so it turned out, trying to get a high-quality OpenFlow agent that could manage all of the hardware, that could work with the things that we wanted to do, the things that we knew the underlying hardware was capable of, wasn't really feasible in the time frame that we wanted it. And I'll talk more about it. But so it's not so much this that why we ended up going into bare metal. Let me not steal everything from the slides coming up, but it's a good question. I'll breeze through these because I get the feel that everybody is fairly SDN aware, right? So the idea is you decouple of control from the forwarding plane, you reduce the number of management touch points. The exact number of data paths to control is a network design question. It depends on what you're building. And OpenFlow does not imply a single point of failure. I have had this question for the last 6 years. You can do load balancing by having some of these line cards point to one switch and some pointing to another, or you can do failover. These are all standardized things right now. And this works exactly like the way a chassis-based system does. So if you imagine these are line cards and the controllers are supervisor modules, if you lose one supervisor module, it can fail over to the other. Yes, it's a hard engineering problem, but there's nothing different about it. There's nothing structurally difficult about it. How many people actually care? I'll just skip this. I think everybody has seen enough SDN. This is where things get much more interesting. So how many people have actually done low-level ASIC programming, just out of curiosity? That's actually much better than I thought. I'll say like 20% of you guys. So the initial versions of OpenFlow only exposed one table that was about 2,000 entries or so. And the reason why they did this was twofold. One, it was the most flexible table. You could match on the most different packet features at the same time. But two, it was the part of the chip that was least used when the rest of the routing software ran. The rest of the L2 and the L3 standard routing software. So if you were a large network vendor and wanted to protect your existing software implementations, your existing software investments, this is the part of the chip that you could, if you wanted to implement a checkbox feature of OpenFlow, something that was not terribly useful but could meet the checkbox, this is the part of the chip that you would expose. And this is the part that people use for ACLs, and most people don't deploy that many ACLs, and so it was probably okay. Because this was so small, it forced the controller to just-in-time insert rules. It would only insert the rules that it absolutely needed. And because of that, this just-in-time reactive insertion, it would actually cause all sorts of scaling problems, both because the actual table size was too small, but because also, flows and forwarding rules were actually getting inserted just as packets were showing up, which caused all sorts of problems and weird delays and weird losses and also weird scaling problems. What happens in practice is there's actually lots and lots of tables on these chips. there's tables that manage VLANs, there's tables that manage just L2 entries, that just manage L3 entries, there's tables that happen after the mirroring process happens. These are much bigger. These tables get up to hundreds of thousands of entries in practice. And this is actually how your network runs today, right? So the routing software that you run on your switches or the switching software populates these tables to scale to the network that you have today. So if you have, this is back to your question, sir. If you have complete control over the software on the box, you can expose these tables up to your controller to do whatever you want with. And you can actually build a real solid scalable solution. Without control of this box, you're now talking to the network vendor, asking them, would you please, sir, commoditize your hardware? Which that's a hard conversation to have. And I will repeat, OpenFlow does not imply flow-based networking. Yes, with the ACL table, you can actually install 5-tuple flow style entries, but with the rest of the chip, the more scalable, useful parts of the chip, you can't actually do that. But you can actually do even more useful things with it. And it's the combination of a packet that matches through different parts of this processing pipeline, the things that you can do to bounce back and forth that and manipulate the hardware, that's where you can get the really interesting aspects of SDN, which is, if it was just a switch, I'd only populate the L2 table. If it was just a router, I'd only populate the L3 table. But when you start combining these things, when you have control over the hardware that's independent of the limits of the actual control plane protocols, that's where you start to get interesting things. So I was talking about in a recent blog using the L3 table to do ECMP-style spraying of short-lived flows, but then using something like SFlow or some other traffic techniques to detect long-lived flows and steer them by hand using the ACL table. So if you're going to have a backup process that's going to last for 2 hours, and you discover it after a minute, maybe it's actually landed in a bad bucket for ECMP and you're getting packet loss. But with SDN, you can actually say, okay, I know this flow exists. I'm going to steer just this one mammoth flow a different way, combining the L2 and the L3 and then the ACL elephant stuff. And there's just a long tail of things like that you can do once you have control over the complete hardware.
So when you say that OpenFlow does not include flow-based networking, this is only for the reactive case.
So the question was,
maybe you want to explain the proactive versus the reactive case.
Let me explain proactive versus reactive first. Once you, and recall, so when you only had 2,000 entries, you were forced to dynamically, just-in-time populate entries because you didn't know who was going to be talking to who, and you had to be very judicious about how you use that memory. Once you have the full swath of the hardware that's available, you can actually proactively populate all the possible forwarding entries that you would need because you've moved from 2,000 entries up to 100,000 plus. And so you can actually treat the hardware the way the network does today, which is to say, when a route lookup happens in your hardware, the router doesn't say, hold on, let me go look up to the slow path and figure out what I'm supposed to do with this packet. The slow path is actually pre-programmed the route into the hardware, and then things just go at line rate, and you get the performance that you expect. And so, back to your question.
Yeah, so when you say OpenFlow does not imply flow-based networking, that's only for the proactive case.
So let me clarify.
Some people are still using reactive OpenFlow, right?
It is true that some people are still using reactive OpenFlow, and it is appropriate in a small set of use cases. For example, I talked with people at Caltech and the Super Collider people at CERN. And so they only have elephant flows. And they have like 3 or 4 flows a day, and they last for like a couple weeks. And in that environment, a reactive flow is fine. But there's nothing inherent about this. You can do flow-based networking with OpenFlow, you aren't required to.
Why is it that the other tables were not exposed? Was it more difficult to synthesize from a flow action pair model into those?
No, so 2 reasons. One is the people who had access to the boxes had the existing software that they wanted, investment that they wanted to protect. And 2, it's actually very difficult to virtualize these tables. Right, so the ACL table is actually fairly straightforward to implement. Because the ACL is a TCAM, you can divide it in half, and you can say, OpenFlow gets the top 1,500 entries, and the standard ACLs get the bottom 500. A lot of these, the rest of these, are not TCAM. They're different types of CAM and different types of memory. And the idea of, so if you imagine you implemented your L3 table as a hardware trie, That's very hard to virtualize. It's very hard to say, I'm going to provide this hard isolation boundary between OpenFlow and non-OpenFlow. And so they're actually doing a lot of very technical, hard things to try to get OpenFlow and non-OpenFlow to live together. And my claim is maybe that's a solvable problem, but it's going to be very difficult with the existing ASICs. What my company did, and I'll talk about this in some detail, is we decided with bare metal switches we could actually swipe the entire software and make it 100% OpenFlow. And once you do that, you can actually get the scale and the reliability by having control of the complete hardware. Does that make sense? Sir?
In your example, how will you identify elephant flow?
As I mentioned, there's all sorts of things that you can do. You can monitor counters, you can use SFlow, you can use NetFlow. There's all sorts of other things you can do. But that's a safely separable hard problem.
So in your example, okay, we can control the tables and all those things, but how will you control the pipeline?
This is the pipeline.
So what if I have to swap the pipeline? I need to do the filtering before L3?
So this pipeline is baked into silicon. And as a software guy, I cannot swap the pipeline. If you want to swap the pipeline, there are hardware companies that would like to talk to you. But I mean, it's like saying I want to define a new instruction on x86. It just you can't do that.
Have you seen any examples where pipeline is a limitation?
So yes and no, right? So here, let me. If people will indulge me on a little digression, so. What the different points on this space represent really are different forwarding technologies, right? So in x86, there's no pipeline, right? You have, like I said, there's a pipeline in x86, but it's not a restricted thing. It's a complete Turing, complete machine. You can do anything you want with a packet. So there's no pipeline restriction here, but there is a bandwidth restriction, right? And to be fair, the slide's actually a little bit outdated. With DPDK, you could even break 100 gig and things like that. With NPUs and FPGAs, NPUs might have a pipeline. FPGAs, you can build your own pipeline. These things are inherently more programmable than the ASICs that are on the next step. And so, the pipeline here is not the limitation, but you have more bandwidth and it's harder to program. Once you get into an ASIC, you actually typically can't change the pipeline. Some of the ASICs have some level of programmability, but usually the pipeline is fixed in some order. And once you move even further down, you get into crazier things where you have clusters of ASICs inside a box and things like that, and that becomes even harder to program. And so, to answer your question somewhat indirectly, for the required bandwidths, the pipeline almost can't be the limitation because you can't change the pipeline to meet the required bandwidths. And so a lot of what the value add of my company and what I spend a lot of my daytime doing is reading the low-level hardware details of how do I squeeze every last bit of performance and flexibility out of the chips as they exist now. Now that said, there is an increasing number of startups that are trying to build more flexible pipelines. Was there another question?
So, in the modern OpenFlow design, do you mean to say that all functionality should be exposed and controlled by OpenFlow, and the hybrid mode that the basic OpenFlow came up with might not be a good option?
I don't think I said that. Let me say something I think that answers your question, but it is a little bit different. So, in the bare metal switch case, a company such as Big Switch can provide 100% of the software that runs on that box. So anything that the hardware is capable of doing, we can expose to the controller. What subset of that we do depends on the application, depends on the use case, and things like that. Now, in the pure OpenFlow world, all that you can expose is the letter of the law, what the specification says. And there are some things that we do on top, and I'll talk about this a bit, that don't belong in OpenFlow. For example, the upgrade semantics and things like that, but are still useful to have on the switch. More questions, or keep moving? I'm happy to discuss all of this. I am paid professionally to talk about this stuff, and I find it really interesting. So happy to take more questions. But
is this solution tightly coupled with the Broadcom, or can it work with any?
Let me punt that off to a couple slides from now where I have an architecture diagram. The short story is, I spend a lot of time trying to make sure it's not tightly coupled to any one specific ASIC, but inherent to doing what we're doing, you are low-level programming the registers, so we have a hierarchy of APIs to try to decouple things, but that bottom level is very tightly coupled to whatever the low-level ASIC is.
So it's no more an OpenFlow.
Say again?
It's like a closed flow.
No, let me come back to the architecture diagram.
So do you translate it to OpenFlow rules and then map it onto the device?
Yes.
Or do you bypass
it? Translate to OpenFlow rules and then map onto the device. So let me go on a slightly different tangent, and I'll come back to this when I get to the open source software. And you'll see, actually, not only is it open, it's actually open source.
So in a sense, then the smarts is in translating it to OpenFlow rules.
Yes, exactly.
That's what the software provides.
In the controller.
That's what you are providing. You're providing an alternative to the software where the real value is.
Well, so there's two levels of smarts, and this is actually why OpenFlow it shouldn't be technically difficult. So there's creating the rules at the controller side. OpenFlow is really the wire level marshalling and unmarshalling of these rules, and then there's mapping those rules onto the hardware. And so one of the reasons why, I'll skip this and come back to it.
When you said marshalling the rules, you mean ordering them?
No, I mean actually putting them out on the wire. So this is the software diagram of everything that exists on the switch for us. Let me walk you through the color coding real quick. So there are two open source projects that you might be interested here. And they're separate for a reason. So Switchlight is the name of the commercial chunk that we sell as part of our product. And so it is composed of the Indigo OpenFlow agent. So this is a OpenFlow agent that you can download, and it's all open source, except for this purple piece, and I'll come back to the purple piece. Tarnation. And then everything that's this, it's supposed to be light blue, but I'll call it more of an aqua. That is the base platform is part of an open source project that we started recently called Open Network Linux. And so the idea behind Open Network Linux, and I've got some more slides on this, is it is a Linux distribution for switches of this type. So we couple all of the drivers that you might need, a bunch of useful utilities. It installs with ONI, if people remember from either Open Computer or from JR's talk, and a whole bunch of the build environment. So it actually builds for a whole bunch of these switches across a whole bunch of different processors. So there's the base operating system, and then there's the OpenFlow agent. The purple piece here, where's my little mouse? The purple piece here, this is the piece that we can't open source because it ties to these closed SDKs that we don't own. So this is, the Broadcom SDK, the Marvell SDK, the Intel SDK. Those are all closed. Not only are they closed, but actually code that actually makes calls into those SDKs also have to be closed. But what we've done is created an abstraction layer so that everything that's orange there, anything that you wanted, if you wanted to build an OpenFlow agent, could tie it down to real hardware. You could actually take and do that. So all of the communication between the controller and the switch agent, at least the top half of the switch agent, is all in open source. So all of the extensions that we've done to OpenFlow, if you wanted to port it to your own hardware, and I'll talk about that in a second. If you wanted to build a vSwitch, you could do that. Although we have an implementation of that purple block that talks to x86. We actually have a separate implementation that talks to the OVS kernel driver just to get good performance. So we can actually have another flavor of OpenFlow as a vSwitch. And people have actually ported this to a number of different silicon platforms. So to your question, sir, about how tightly coupled are we to Broadcom, that purple block is our coupling to Broadcom. But we have purple blocks for a bunch of different pieces of hardware.
This, in some sense, conforms to that left side of your picture, which is the traditional model.
Except 100% of this, so in the Big Switch controller, we still have the application and the platform as one solution. And the difference here is this operating system isn't coming from the people who built the hardware, it's coming from the people who built the controller. And so what ends up happening is, I talked to a customer, they said, wouldn't it be great if the solution, not being able to decouple the parts, could do X, Y, and Z? Then I go back and we develop what it would take on the controller side to do that, and then we can go develop what it's going to take on the switch side to do that. And we have teams inside one company and can turn around that very quickly. We couldn't do that if we had to integrate with a standard version of OpenFlow that was being provided by the hardware manufacturer.
Yeah, if I add more protocols and everything on top of it, then it sort of boils down to a Cumulus Linux distribution.
Well, and so the reason why we have Open Network Linux separate from the Indigo agent is exactly so that people could do whatever they want on top of Open Network Linux, that you aren't tied to building an OpenFlow agent. And actually what's interesting is, given this model, OpenFlow becomes more of an implementation detail. It looks a little bit like Thrift, or it looks a little bit like Google protocol buffers, rather than an architectural component, right? It's just a way to communicate the forwarding plane changes. And in fact, we even talked with folks at Cumulus about, do you want to just adopt Open Network Linux? And certainly we're talking with other people about that as well.
So if the box is running Linux and it's programmable, why do you even need OpenFlow?
Well, so that's kind of what I was saying. So part of the problem one is the box is programmable if you're under NDA with the switch company. So OpenFlow is a way of people who aren't under NDA with the switch company to write things to this. But let me advance a little bit. Oh, and by the way, we support lots and lots of boxes. We're going to be adding x86 support soon. Open Network Linux, because it's the base of our commercial product, it actually has a little bit of a different feature train, so it actually supports more products, more boxes than a commercial product does, because it honestly just goes through less testing. So just because a box is listed as supported here doesn't mean it will work with our commercial products. But it's a matter of testing, not that we don't think it'll work. I should come back to all this. There's really good stuff here. So you were asking about, what is it like? What if I could just program the chip? So Broadcom did this very cool thing just recently. Who's heard of OFDPA? All right, so I'll call that 6 people. Broadcom has actually published an SDK on top of their SDK. And the difference about the SDK on top of their SDK is the top half of this SDK is actually open. So if you want to do something that was not OpenFlow, you could grab Open Network Linux, you could grab OFDPA, and in my spare time, which haha isn't very much, I'm trying to make it packaged together so you can download them all at once, and actually develop your own applications. And so if you remember the tables that I showed you before, this is actually the tables that Broadcom has chosen to expose. So the tables I showed you before are the things I can get away with without breaking NDA because it's generic enough that nobody really cares. This is actually what Broadcom has exposed from their chip, which is even a subset of the actual tables. So if you Google for OFDPA, you can find this whole programming guide of what you can insert into where. As a bit of a caveat, OFDPA was built to have OpenFlow agents on top of it. So this API actually itself looks OpenFlow-like. It's a local API. You don't have to build OpenFlow on top of it. Although, just so people know, the Broadcom folks and Big Switch actually worked together to port. Remember I had in the previous picture, there was a top half, bottom half of Indigo, where there was like this, the purple chunk that was architecture specific. They wrote another purple chunk to talk to OFDPA. So if you want to have an OpenFlow agent on top of this, you can. You just aren't required to do so. Questions about this?
So what you mean is OFDPA is an OpenFlow agent?
No, OFDPA is a generic SDK for programming specifically Broadcom chips. And the only notable thing about it is the API to it is actually open. So the source code to the SDK is not, but it means that you can go to the GitHub site, download this, and write whatever you want on top of it. If you wanted to compete with Cumulus or compete with Big Switch, you now have all the keys to do that. You don't have to get under NDA with Broadcom. Now, I will tell you that this OFDPA actually exports a significant subset of the normal SDK. And a lot of our work, actually, we have to bypass the SDK and program to the raw registers. So you wouldn't compete very well with us or Cumulus, but at least you could start, right? Which, if that's not open networking, I don't know what it is. Now, at the same time, everything that's in this color here is still closed. So it's not open networking in the way that your Linux networking stack is open. So it depends who you talk to. When I pitched this to a bunch of folks from Red Hat, they still panic. They're like, this is not open. I'm like, I understand, but it's more open.
I guess I would like to get back to my previous question because of this. But this is, to me, seems maybe in a naive way, kind of like just a closed source driver in Linux and PC world.
That's exactly what this is. Yeah, that's exactly so. And apologies to jump all over the talk, but I'm going to bring it all the way back to the beginning.
Sorry, can you repeat that question?
So he was saying, isn't this effectively a closed source driver in the way that you might have a closed source driver for a NIC in Linux? Is that a fair approximation of your question? And so recall that this is why this slide exists, is we're moving networking for this class of switches, data center switches that actually produce a whole lot of traffic, from not very open to a little bit more open. Which is to say we've moved it from it's completely closed, you can't do anything with it, you can't install processes, you can't really log in outside of the shell, to you can actually log in, you can even change the operating system, you can change anything you want, you have source code to everything you want except for the SDK that programs the ASIC, which it's not all the way there, it's not to the top of this picture, but it's more open than it was before.
And I guess that goes back to my previous question, right? Because if your goal is to change the table, I mean, a closed flow box gives you mechanisms to change the table. You just have to follow different sets of rules, and it might be via CLI or SNMP or NMS or some kind of...
So let me repeat your question first for people. So if your goal is just to change the tables, then a closed flow box will let you change the tables, right? And so, one, the closed flow boxes would only let you change one table, not all of them. I mean, it's not an inherent technical limitation. It was just a fact of what they did. And two, it turns out you actually do have to do a whole bunch more to make this operationalized. So, jumping back to where I was. Are people okay with me jumping around? I feel like this is still an interesting and lively discussion, but if people want more order, I can enforce more order. It's just not really my natural state. So, on this box, you have SNMP. There's SNMP on an OpenFlow box, right? But it turns out a lot of people think SNMP is really useful. There's syslog, there's NTP, there's fan, there's things that you want to control here. Sometimes people want to log into this box, much like, have everybody ever logged into a specific line card? Like you do like session 15 or something like that, right? There are times when you need to do that. People want to actually run Chef and Puppet on these boxes. In terms of the OpenFlow agent, like the way you expose tables, which tables you expose. So right now, it is not possible under NDA to expose tables one-to-one, right? Because then you basically violated all of the constraints. So there actually is some abstraction process. So a table that exists in the ASIC doesn't get exposed one-to-one through OpenFlow. And so, OpenFlow itself, I like to say, is actually a fairly high-level language. People want to think of it as a low-level language that solves all things for all people. But the way you abstract a given piece of hardware, you have to make design decisions there. And then, see, this is why I shouldn't have skipped around in my talk. There's all sorts of people that things you're supposed to know before we get here. The question you keep raising is effectively, why can't you just do this with closed flow? That is one of the key points of this talk, and so there's different things that I get at through different parts of it. So let me pick up the sequence from where I started, and we'll keep coming back to this if you're okay with that. Other questions while I'm swapping around more?
So what is preventing the chip vendor from exposing those APIs in the future?
Pure financial greed. No. So, I mean, they have invested countless amounts in R&D, they believe is a commercial competitive advantage to not let their competitors understand the inner workings of their chip. And so it's not at all a technical problem. In fact, I have complete access to all the technical specifications, I have complete access to the source code for the SDKs, but I have that under NDA, and a sniper follows me around, and every time I talk like this, I need to be careful what I say. I got one left, thank you. But it's not a technical problem, it's purely a business problem. They're trying to protect their investment. So
how are you providing value over that? Are you exposing all the tables which the hardware vendor did not expose? Is that what you're trying to?
So the question is, how am I providing value? Am I exposing all the tables the hardware vendor cannot? And the answer is, the Big Switch is providing value all the way at the top of the stack, which is, I'm not going to make this a product pitch, but we have a network monitoring product called Big Tap. And so if you want to more scalably monitor your network, this is a good solution for you. The fact that there's SDN and that there's tables and there's open source under it is just completely irrelevant for you. The only reason we've actually open sourced a bunch of this is A, to ensure that people know that they aren't getting locked into a vertically integrated solution, and B, there's actually a lot of benefits for working in the community. Our partners grab the open source code. They build, a lot of our partners have ported our Indigo OpenFlow agent onto their hardware. With the Open Network Linux bit, the bit that abstracts over the fans and CPUs and stuff, our hardware manufacturers have actually started porting that to their new platforms. And so there's actually a bunch of value from a pure engineering standpoint for us to having the bottom bits be open source, because all of our value is in the controller and in the solution. Let me put it differently. The people in this group are atypical. The fact that we can have this conversation, you can understand what I'm talking about, means that you are in a very, very small fraction of the world. Hats off to you. It makes you guys very smart. That's good. But most people buying networking products don't even want to think about this level, much less even try to program to it. And so, if you're a do-it-yourselfer type, then we should have a great conversation about fun things you can do with this. But if you're a customer that's looking for an end solution, the value is actually all the way at the top of the stack for how it integrates with this entire system, not at the lowest level or even at the tables. Does that make sense?
Make money only off of the physical instances that they sell, or do they make money off of you guys as well, for every instance of the OS running on this? Because they're partnered with proprietary.
I'm trying to decide if I should answer that. I mean, they sell the chips, right? They're Intel. They make money off the chips, not off the rest of it. I don't think that's a violation of NDA, so we'll edit the video. But well, because there's somebody out there who's Broadcom is charging for their stuff, and they're like, oh god, Big Switch isn't paying for it. Why am I? Okay, we're editing the video. So if you take one of these switches apart, there's a whole bunch of different things in it that are kind of relevant. There's the actual chip that we're talking about, the Broadcom chip or the Intel chip or the Marvell chip or whoever else's. There's the box, like there's all the sheet metal and the PHYs and stuff, the power supplies, all of the PCBs. There's some sort of drivers that work for the hardware. There's the operating system, and then there's the application on top, whether this is an OpenFlow agent or whether this is your routing protocol or something like that. So this is roughly, if you were to break this box down across the ecosystem, what it looks like. And so if you take these 5 layers, historically networking, when you bought a product, like one company would build all of this, right? Cisco builds the chip, they build the box, they built the drivers, they built the operating system, they built the application on top. They just built everything. And a lot of that was because even 15 years ago, networking was not so big. There was not so many boxes being sold that there was actually the commodity of scales that allowed this to be horizontalized. And more recently, what started to happen is when you buy a box that has a big brand name on it, they're not building all of the components. They might buy the chip from somebody, they might outsource the box building to somebody else. They might not even build all the software. There's all sorts of software companies out there that sell only to big name network manufacturers so they can outsource the software as well. So this market has effectively horizontalized. There's actually a large, fairly complex ecosystem that brings all these components together that results in a box that shows up in your network. And then if you look at how this compares to what I will call the traditional OpenFlow model, this is the closed flow model. The idea was that the hardware vendor would actually sell an OpenFlow agent with this, and then you would have an SDN controller and an application on top of this. This is the question we keep coming back to. This is the thing, and I'll talk more about it in the next slide, that these didn't really work out for us. And then what's different about what I'm talking about here, this bare metal vision, is you buy from one company an integrated box and chip, because that's the hardware. That's pretty hard to decouple. Although the server people eventually did it by standardizing the chip interface. We're not quite there yet, but at least right now you can buy just the bare metal, and then you can actually layer all the software on top of it. And you can either layer our stuff or you can layer somebody else's stuff. And you can buy these things differently. So when I talk about bare metal, this is the thing that I really mean. And so why didn't we go down the original OpenFlow ecosystem model? And so part of the issue is it's really technically hard to build an OpenFlow agent that is all things to all people. By which I mean you build an OpenFlow agent once, and it supports all the possible applications that you want to support on top of it. And this is back to what I was saying earlier, that an OpenFlow agent is actually a relatively high-level API relative to what the hardware can do. And to talk about what does it mean for something to be an ASIC? So an ASIC is an application-specific thing. It is not a Turing-complete machine. If you wanted to do something it wasn't programmed to do, it's not like you can drop to software and emulate it. It is just not possible on this box. It's not like it goes slower. It just doesn't work. And so trying to create an abstraction across a whole bunch of application-specific chips is an inherently hard thing to do. If you take a product line from one company, take Broadcom, take Intel, something like that, and use the SDK on top of it, there are things like, so you figure those chips are not too different, right? They're built by the same people, they do roughly the same things, they have the same rough feature sets. Even those have a hard time abstracting across that limited set of things. And so the idea that you can build an OpenFlow agent that works uniformly, not just across all forwarding hardware, ASIC and otherwise, but also is useful for all applications, that is just an incredibly hard problem from an engineering standpoint. That's not to say that I have any concerns about OpenFlow, the wire protocol. With a couple extensions through the standards extension mechanisms, you can communicate the intent that you want over the wire. But the idea that you can build an OpenFlow agent that I can use to build any product that I want is the thing that we just never really saw. And we actually had some people work really hard with us trying to get that. We had companies that said, F it. I'm going to put dedicated people on this. We're going to work on an accelerated schedule. We usually work on a 6 months release schedule. We're going to work on a 3-week release schedule, trying to keep up with your team and the feature velocity that you want. And just because of remote offices, different companies, different politics, different things, even these companies weren't able to keep up with the feature velocity that we wanted for a specific application. And so what we did was eventually went with a switch-lite model, which is to say we actually customized the software on the switch to the application. So when you actually deploy one of these systems, what happens is you turn on the controller and you plug in a switch and you turn it on, and the switch actually net boots off of the controller. So the switch gets a version of the switch hardware, a switch software specific to that application. And that's a fundamentally easier problem because you know what the hardware is and you know what the application is. And let me revisit the point of economic incentives. In the top model, you're asking somebody to do something that is potentially intractably hard to solve. So we'll call that difficult from an engineering perspective, to be generous. That only comes out of their bottom line. You're asking them to commoditize themselves. Whereas in this model, the controller company, the people who are actually going to make money by selling more of these things, are actually the ones who are incentivized to provide a good quality OpenFlow solution because we're the ones who benefit from it. And it's one engineering team we get the higher feature velocity. Question?
Can you give an example of some of the customizations that are necessary for some applications?
So if you take our tapping product, one of the things that we do, and it seems weird, but it actually makes a lot of sense, we have an OpenFlow message to disable CRC checking on a port. And so the idea is if you have a CRC error in your production network and you dump that to your tap network, you don't want the tap network to drop that packet because it's malformed. You want to forward it onto the tool so they know that there's a problem. There's a number of things like that. All of our extensions are actually all open source for what it's worth, and I can point you to them.
And these all take the form of extensions to the wire protocol?
Yes. Now, it is worth saying that the OpenFlow protocol, particularly the 1.3 protocol, is heavily underspecified, and how many tables you present and the form of those tables and the order of those tables are not specified by the protocol. And so there's even a fair bit of liberties within the OpenFlow spec that we found have been required to make to build a useful product. There was a question over there? Okay.
I also wanted to know what are the typical example of extension you had to do.
So if there's time and I can get network connectivity, which might be more time than we have, I could just point you to the website. We have all of our extensions are in open source. You can look through them to your heart's content. There's a question over here.
How relevant is OpenFlow as a protocol? I mean, once you have an open platform, you can put your own agent on it. The server guys you run a Puppet agent or a Puppet controller, you just pair the two, and whatever you run between them is your own business.
And that was the point that I made a little bit earlier. When one company is providing both sides of the interface, the actual underlying protocol is less relevant. That said, if I were to design a protocol to do this from scratch, it would probably look like an extensible TLV-based protocol, which by some definition is what OpenFlow is. It's not 100% there, but the difference between where it is and where it wants to be is what the extensibility working group is working on. Now, would I have done it with Thrift or Google Protocol buffers, knowing now what I know now, just because there's code written to do that? Maybe. And in fact, I'll talk briefly about this program, Loxy, that we wrote. It's not possible with protocol buffers or Thrift to write something that compiles down to the actual OpenFlow wire protocol. So we built a tool to do that for us. So you could think of it like protocol buffers for OpenFlow. So given a high-level description of the protocol, we can compile to a C library, a Java library, a Python library, and a Wireshark dissector. So anytime we define a new extension, we automatically get those swath of languages in the Wireshark dissector.
So you're saying if there was a one-to-one coupling between you and the switch, you wouldn't need an open protocol. But the customer might desire, might look at OpenFlow as a way to have multiple vendors on top.
So let me dissect your question if I can. So it is actually, even if it's big switch code on the bottom and big switch code on the top, it's still of value to customers to be able to, for debugging purposes and monitoring purposes, to have an open protocol be there. So what Peter was at, so if you imagine, higher end customers will debug OSPF messages and make sure that their network is okay at that level. What Peter was saying is, does it have to be OpenFlow or can it be some other protocol? That was the other question. Whether it was Google Protocol buffers or Thrift or something like that, it was more about the marshalling and marshalling that matters. But yeah, I absolutely believe this should be an open protocol. Sorry, does that answer your question?
It mostly does. The other protocols you mentioned, I'm not sure would work very well for multiple controllers, multiple applications cooperating, managing one switch. I think that OpenFlow does allow them to cooperate.
Well, and so that's the top part of this, which is to say, that's definitely the OpenFlow vision, that I can have one company produce the OpenFlow switch and another company produce the OpenFlow controller. Like, that's the vision, right? And what I'm telling you is that vision is impossibly hard. Impossibly might be a difficult, impractically hard. And so basically you end up with this thing that says, I want this agent to be all things to all people, right? I'm going to build the agent one time and it's going to work with every controller that can come down the road. And maybe that's possible, but I tried really hard for 5 or 6 years and couldn't do it. And it's because it's hard to abstract across all the hardware. It's hard to understand what the applications that are coming down the pipe. We may eventually end up there, but at least for right now, I think that's difficult. Sir, you've had your hand up.
If you'd be so kind as to indulge the ignorant, could you jump up into low Earth orbit and tell me, what are your customers doing with this and why?
So I love that question because when I give talks like this to a general audience, I try to talk about the technology because I'm not supposed to talk about the products, but if people want me to talk about the products, then I'm very happy to. We have 2 products. One is a monitoring solution. So the idea is, imagine you have a production network. You don't want to touch that. That is holy. It is sacrosanct. It does what it's supposed to do. You want to more scalably monitor what's going on there. So there is a growing ecosystem of tool vendors. So that is people selling packet recording devices, people selling intrusion detection systems, people selling quality assurance. So if you have VoIP problems, there are boxes that will tell you exactly what's wrong. And then so you have this weird problem of you have a span port on your switch and you have 8 different tools across 3 different departments in your company that want to consume that traffic. And you don't have just one switch with one span port, you might have 50 switches with a whole bunch of span ports. And so what you need is an actually fairly sophisticated tap monitoring network to connect all the span ports to all the possible tools. So that is one of the things that people have been doing with our products, and that's been incredibly successful. Our largest customer, I think, is deployed across 15 data centers and is dumping tens of terabytes of traffic with that.
So this is all east-west stuff?
So that's actually No, so that's pure monitoring traffic. So we're not interfering with the source and destination of the traffic. It gets installed either in a data center in an east-west situation. It gets installed in a north-south situation. It can even get installed in a DMZ. Different customers are using it for different things. So anywhere that you might want to monitor traffic, you can actually more scalably, more efficiently monitor that traffic with this. I did say there were two. Second product is not launched yet. We're going to launch it later this year. It is. We've been talking about this off and on. I'm trying to be careful about what to say and what not to. So remember how I said your production network is holy, it's sacrosanct, you don't want to touch it? If you believe that, then the monitoring product is what's for you. But our second product, our Cloud Fabric product, is for controlling that production network. So if you have a data center that has lots of east-west traffic, it has lots of north-south traffic, you've got multi-tenancy policies you want to easily enforce, that's what the second product is for. And I'm happy to keep talking about this, but my guess is the appetite for hearing the Big Switch product pitch is going to be light.
So regarding to your second product, it is called Unified P plus V. So I'm just curious, so if this is based on the tunnel or not?
So, thank you for repeating our marketing terms. Thank you. So just so you know, the unified P plus V is to control the physical and the virtual, the P and the V, from one place. And at least the current form does not use tunnels. We found that's actually not as needed as people claim it is, at least inside one contiguous pod. And then you only use tunnel to get between pods.
Going back to the earlier topic of the OF agent. So what you're saying is it's difficult to build an agent which works across all hardware. Okay.
All hardware and for all applications.
So you're saying for the same hardware, if it's a different application, the agent has to change. And that's what you do.
Certainly life is easier if it does.
So even in a scenario where, let's say, Cisco builds their own agent, you build your own agent, somebody else builds their own agent, you're saying the OpenFlow protocol itself is still not sufficient to talk to these different agents?
Basically, yes. So if you were to take either of the products that I was talking about that work with our OpenFlow agent, you could not get it to work with other people's OpenFlow agents, even without the extensions. Because, and remember what I was saying about how which tables you expose and in what order? That's the thing that's not specified by the OpenFlow protocol, but that is the most important thing that you can get out of the chips. And the reason, and it's not like the people who work on OpenFlow are dumb. I'm a person who works on OpenFlow. The answer is that the hardware does it so differently. FPGAs can produce any tables in any order that you want. x86-based chips can do even more than that. But the ASICs have this very restricted list, and so there's even an internal tussle for, is OpenFlow for controlling one type of forwarding hardware, or is it for all types of forwarding hardware? These are actually architecturally hard questions to answer.
So what could be a typical, so if I took two agents who are OpenFlow agents, like they're just implemented by the book, like they don't have any extensions. So what could be the potential problem by this ordering of the table different in the two ASICs?
So let me go to, so, but can I give an example that doesn't violate NDA? So not even my NDA. I had no problem violating my NDA, right? We can edit the film here, but so I guess an easy example that I mentioned is the way I showed the processing pipeline is that you go to the L2 table and then the L3 table. That is true for one class of chips. It is absolutely not true for other classes of chips. Another thing is, do you have the ACL check after the L3? So if you imagine, packet shows up at a chip, it says, oh, this is to a MAC address, which is internally one of my router interfaces. Let me apply the L3 processing. And then after that, after an L3 decision is made, then you imagine the ACL table has a chance to say, well, actually, that's to a place that I actually have a drop rule for. Let me drop that packet. The ordering of that actually affects the logic that you would push down onto the types of applications that are possible really get changed depending on the order of operation that these things happen. How many rules do you have available? how flexible is your ACL entries? Can you match on which fields can you match on? Can you match on like the inner tag of an MPLS stack? Those are the things that really get different between different hardware, and you can't. And this is the problem with being an ASIC. I as a chip can't tell you I support something that I don't, knowing that I can just fake it under the covers with software, because at the processing speeds that we're talking about, either it has to be fully line rate hardware supported or it just doesn't work. Does that make sense? A little bit? I mean, it's a bit of a vague example. Apologies. If we had the time and I could jump you through chip documentation, I could make it a little more concrete. But
why is it done in the server, like whether it's AMD or Intel? You can put a OS over it, right?
Why is it done there?
Yeah, so different NPUs you say that it's not possible to do. But in the server side it is done today.
So, I mean, so the question is... Oh, Christos. You're talking over my talk, Christos. So let me see if I can repeat the question and make sure I understand it correctly. So you're asking why is it that you can replace all of the software on an x86-based machine and maybe not all of the software on an MPU or an SoC or an FPGA? Why do you have these binary chunks? And the answer is it's not a technical problem, right? It's a business decision. The companies that have invested in this hardware believe, and I think honestly believe correctly, that they don't need to open up these devices. They're making a lot of money, and if they do, and this is the part where maybe we agree, maybe I agree, maybe I don't. If they do open up these devices, they might actually lose competitive advantage. One of their competitors might understand something about the chip design that helps them compete better, right? And so what actually is happening, and this is hats off to Broadcom for pushing OFDPA. What's actually happening is they're actually going through the fairly difficult exercise of saying, do I really lose competitive advantage if I give away some amount of this information? Because I'm actually enabling a whole ecosystem here. And so, just historically, these companies haven't done it, and that might be sufficient reason for them to keep it closed. But at least some of them are going through the exercise of deciding, can I open some of this up? In the back.
To answer the issue you just brought up, listen to somebody like Harry Saul talk about the antitrust suit that he administered with 2 other people against Microsoft. Microsoft started on the page of, oh gee, it's got to be a secret, and the court said, no more. You got to open it up. By the time they were done, they were loving open it up, and it was better for them. And I think these chip guys are stuck in the same quagmire.
Well, and practically speaking, it costs them money to open it up because it's just different, and there's no money to be made in opening up. At least in the short term.
One of those guys talk. You're parroting what they went through with Microsoft, and they had the Supreme Court backing them up, and Microsoft had to play ball.
Well, and none of these chip manufacturers are large enough or having a large enough swath of the thing, at least in my opinion, to have the monopoly argument played against them. But maybe I'm wrong.
You're missing the point. Microsoft started out hating it and ended up loving it. Because at the end of the day, it was better for them to be open than to be closed.
I believe that. I am not an employee at any of these companies. They are sick and tired of me hearing from me about how I think they should open up their things and the financial opportunities for them to do so. So I absolutely agree with you. These are just large companies, and they are actually even changing a little bit over time. And we'll see where they do end up. So
we were talking about examples of what might break, what might not work. Is another example a situation where it appears that you have a lot of table space to add a lot of flows to solve a problem, until you actually try to put the data into it, and that depends on what you're actually trying to download.
Well, and so you're more right than you know. Let me just repeat the question. So it might appear that there's an amount of space to do something, but when you actually populate it, you find there's less. So a very typical hardware trade-off here is to actually have these tables share the same underlying backing memory. So you might be able to get 100,000 entries in each of these tables, but not all at the same time. And some of the design trade-offs to get that, what is the ratio of an entry in this table means this many entries in this other table is actually very complex. And even with the hardware design docs and having 100% of the information, it's kind of hard to characterize. And certainly, trying to characterize it online in a protocol like OpenFlow that's standardized, that's a really hard problem. And that's one that, and I was in the room when we were working on that, we just punted on that. We just said, that is not a solvable problem. So I absolutely agree. That's another good example.
So is it that these ASICs are not really tuned to an OpenFlow way of working? I mean, would we in the future have ASICs which are more amenable to, a OpenFlow kind of protocol?
So the question was, is the ASICs are not tuned to OpenFlow, or is in the future we're going to have something more that will fit that way? There is certainly a school of thought that way, and there are actually companies coming down the pipe building new ASICs that are more like that. I actually think it's almost the wrong question. So in my mind, OpenFlow should do a better job of exposing what the hardware does, not the other way around. And of course, there'll be a little bit of give and take. And it's not that OpenFlow isn't good at exposing these things, it's that the internal processing dependencies, the internal hardware dependencies are really hard to describe programmatically, right? So the documents that I have for these chips are like thousands of pages long. And for the idea that we could encode those requirements and those complex dependencies on an online protocol and have a computer on the other side parse and make sense of this to decide, if I want to do X, Y, and Z with the chip, does this chip support it? That's actually a hard problem. It's a technically very hard problem. I mean, a lot of what we spend our time doing is roughly low-level assembly programming to these chips. And people say, well, of course, we're just going to write a compiler to do that. Well, compilers work because it's not a question of, can you do this? It's not about correctness so much. It's a resource scheduling problem, because I know that I can do, if I want to add two numbers, I can use any of these lists of registers. But it's not like I have to worry about chips that don't support addition. And how do I fake addition if I don't have it? It's a fundamentally different problem.
Would anything like a middleware type software help us besides APIs?
So that is what the OpenFlow agent is supposed to be.
It's supposed to be that. But is there anything that would, a real middleware that would open that up across the board?
For the applications I've looked at, the answer is no. That in order to leverage the real underlying part of the hardware, you actually have to program them at an ASIC-specific level, and that there hasn't been a way of abstracting across that.
So Rob, we're running short of time.
Okay.
So go more focused.
Be more focused. Damn it. What do I want to hit in the remaining time that we have? So fabrics are really useful. You can use them for connectivity. You can use them for, so basically this is product number one, this is product number two if you want to do tapping. We actually have this internal, I don't want to call it a product, it's more of an internal dev test thing where we've turned fabrics into a patch panel. So if you imagine you've got a whole bunch of switches that you're testing, you've got a whole bunch of packet generation stuff, and you want to programmatically supply the connectivity between these things. We've actually, using our fabric, built this up. And so the idea is that test by test, we can program subsets of the fabric to say, all right, now do the all pairs test, now do this test, now do that test. And it's talking to the packet generation as well as the topology that we can build virtually with the fabric.
Back up to your first slide. What was the first product?
This is the multi-data center multi-tenancy case. So the idea is you've got a bunch of servers, you have some sort of policy about who can talk to who. Maybe these servers host VMs. That's the P plus V part of this. Maybe you have quality of service that you want to assert between these things. Maybe you want to integrate with a hypervisor or VM orchestration system like OpenStack. You want a single point of management for this entire system. And again, I'm trying not to make a product pitch, certainly not for products we haven't launched yet. But
so what are the boxes
so these are just 1U switches. So in practice, this ends up being probably a 48 by 10 gig switch with 6 40 gig uplinks. And these end up being pure 40 gig switches, probably with 32 by 40 gigs on them. These are all bare metal, yeah. So each one of these, so a leaf and a spine, if you haven't heard that term, refers to where it appears in the topology. But these are all bare metal 1U data center switches.
So compared to the traditional model of the vertically integrated solution, looks like the SDN alternative also, the software is getting vertically integrated. For example, Google has its own SDN, but they own all the from leaves to spine. the proposal, what you have also, the software gets vertically integrated. So what is the benefit? Is it the hardware becomes?
So having to, being able to buy the hardware separate from the software is a first critical step. So it means that if you buy the big switch solution and you decide it's crap, you won't, it's good stuff, but if you decide it's crap, you can throw out the software and buy the Cumulus stuff on the same hardware. Or you could throw that out and put the Pika 8 stuff on the same hardware. Being able to, much like you buy servers, right? You can buy a server and put Linux on it, you can put Windows on it, you can put Mac OS on it. Now, Mac OS is still a fairly vertically integrated solution. Yes, there are some APIs that you can build applications on it. People have ported reasonable applications on it, but it's still reasonably vertically integrated. Having a hardware-software divide, at least to me, makes sense.
How often do you expect that to really happen? I mean, even in the PC world, I'm not familiar with people, that they bought a PC with Windows on it and then decided, shit, I don't like Windows, I'm going to install something else.
Because everybody doesn't like Windows. Everybody's smart.
Or maybe different Linux distributions, right?
So, I think, how many people dual boot? A lot of people dual boot, right? So more likely is, people might switch from.
We do.
No,
but
but
I'm talking about your customers and
so customers definitely switch between Ubuntu, CentOS, RHEL, and they switch between those things, and they might decide, yes, I'm going to upgrade to this next new version of something like that, or maybe I don't need the standardized support contract, or these machines were part of a Windows remote desktop cluster, and now they don't need to be, so I'll repurpose them for Linux. So it really does happen, but it's more about the flexibility of it, right? You don't have to, at the purchase time, decide how you're going to use these machines. How much more time do I have, Vikram?
20 minutes.
20 minutes? All right.
On the next slide where you had the soft patch panel, how well is that compared to a layer 1 switch?
So it's a fundamentally different solution. It's cheaper. It's cheaper. You can get up to full bisection bandwidth. We basically turn off all of the L2 and L3 processing. So it really does look like a layer 1 switch at some level. It doesn't have some of the, one of the big things you get at a layer 1 switch is this doesn't provide is, in a layer 1 switch, typically if the device fails, the packets keep forwarding. That's not the case here. But here, if the device fails, we can reroute it through other means. Maybe I didn't say this enough. This is not a product. This is just something we built in the lab to make our lives easier. We actually had people ask us to productize this, and you can imagine trying to do that. But this is just another data point of what you can do with this technology.
Sorry, what do you use it for?
QA. We have a whole bunch of switches. We want to make sure that they all work together. So we actually use our own software to make sure they work together. Yeah.
So there'll be typically same switches, or do you?
Sorry, I can't hear you.
Do you test the interoperability of your
So yes, we do, but that's independent of this. So actually, it's something that I get questions a lot about, and hopefully I can start to wrap up after I've bounced all over the place here. But people say, well, how do I know that your software is going to work with any of the switches that are on your hardware compatibility list? So what happens with our customers is, they say, all right, your TAP product sounds awesome. Let me buy that. And we say, all right, you can buy your choice of this switch or this switch or this switch. And you can get that switch from us. You can get it from a reseller. You can get it. You can find it yourself. Actually, increasingly, you can buy them on Amazon, literally buy them on Amazon. And then they ask us, well, how do you do quality assurance? I don't want to do the interoperability testing. I'm a customer. And I tell them, well, we have lots of engineers that do the interoperability testing ourselves. But they say, well, why shouldn't I buy something from a more traditional network vendor? I don't have to worry about this at all. And the answer is, this is actually the same process the traditional network vendor does. They have either a different team in the company or more likely a completely different company that builds the hardware, and then they do the interop testing and all the quality assurance in-house. And so we do exactly that same thing. Does that kind of answer your question? All right. I think I will just obnoxiously flip through So this is the Switchlight architecture. This is Open Network Linux. Go to the website. It's under construction only because it's me with VI making it work, so it's not terribly pretty, but eventually it will get pretty. We support a whole lot of hardware. There's a whole bunch of stuff that composes down to a whole bunch of different architectures to support that hardware. It's interoperative with ONI. I'll skip this. And of course, don't forget about our open source controller, Floodlight, to actually manage this whole stack. So I was just obnoxiously jump to my conclusion slide. not the subtlest of endings to the talk, but so yeah. Big Switch builds SDN solutions on top of bare metal hardware. We have 2 commercial products, Big Tap and Cloud Fabric. Cloud Fabric is still in beta now. It's not going to be launched just yet. SDN has evolved significantly since the early days at Stanford. We've gone from single table to multiple table. We've gone from reactive to proactive control. We now have, with bare metal switches, we can actually control 100% of the software on there, making our own OpenFlow design decisions. We have a lot of open source projects that you can play with if any of this is of interest to you. And this is the group where open source might be of interest to you guys. Starting at opennetworklinux.org is not a bad place to start. And if any of you have any more questions, I will continue to answer them until Vikram kicks me out. But thank you guys so much for having me. I've definitely enjoyed this. Although I am out of water, so it's fine. Any more questions?
So can Switchlight work with OpenFlow controller?
I believe so. There's no reason to think it shouldn't. I haven't actually tested it. I put it this way. I think people have told me, yes, it does. I don't know. I haven't seen it for myself.
Can a customer write and install their own software to run on the Switchlight platform, say on a Quanta switch or any bare metal switch?
Yes, and in fact, people are doing that with Chef and Puppet and things like that. So a lot of customers have internal monitoring stuff where they have a custom monitoring daemon that they just want to run.
And once on that platform, would they discover that there's additional APIs, additional information that's accessible?
I mean, it's standard Linux, so there's a bunch of APIs available through Linux. But there's nothing special that we add on top of it besides the OpenFlow agent.
But to the switch fabric?
Oh, so talking to the controller, yes. But to the individual switches, no. So if you imagine the switch fabric is logically represented by the controller, and there are APIs to the controller to manage that.
Oh, sorry, I didn't mean the switch fabric. So if I'm on...
Oh, you mean the actual forwarding chip?
The chip, yeah.
So no, basically it is not really possible to have the chips be controlled by multiple entities without them being aware of each other, and that's what gets messy. That's what's actually hard about the original closed OpenFlow solution.
What about read-only?
Read-only is definitely possible, although all the information is available read-only from our controller as well. Yeah, so, I mean, why log into each individual box when you've got a controller that does it for you? Other questions?
Yeah, in the slide you showed, right, x86, then FPGA, then switches, then finally the big boxes, the 10 terabit kind of boxes. So
yeah.
What will it take to implement your model in those 10 terabit or the biggest box?
Absolutely nothing different from a technical standpoint. It's again a pure business thing. So actually, the reality is those big boxes are composed of lots of the little chips that are in at least the data center switches. And in fact, products that we launched just today are actually built on some of the same chips in those in the 1U data center switches.
Yeah, the bandwidth comes from the fabric, and you have already opened up the fabric. Right?
Exactly. And so, so actually, this is very much where Big Switch gets its name, is that you can manage a cluster of devices as if it was one big switch.
Can you speak a little bit about the management, aside from OpenFlow? Do you have any architecture?
So OpenFlow is not really a customer-facing thing when you get the part and parcel solution. We have REST APIs into our controller, and then we have a CLI and a GUI, and both of those are actually REST API clients. So you're guaranteed that everything that you can do with the controller is exposed through REST, because the CLI and the GUI are not special. They just talk to that REST API.
So it's safe to say you're not extending OpenFlow to do management functions?
No. Yeah, that's just not the right tool for the job.
In your spine and leaf model, is the forwarding decision is still pushed from the controller, or it's like every switches they take their own decisions?
So every forwarding decision is made by the controller and proactively pushed down to the switch. So by the time the packet arrives, the switch is making the forwarding decision, but it's basically just acting dumb. It's doing what the controller told it to do.
Both leaf as well as spine? Or?
And both leaves and spine.
Okay, then that might add up to the latency, right, isn't it?
I didn't know.
That might add up to latency, isn't it? Like every packet you take a decision from the controller and...
No. So let me say this again just to be clear. At the time the system gets turned on and a policy gets programmed, then the decision is pushed into the switch well before a packet shows up. So there's no additional latency. Now, this is actually how routing protocols work, right? So you turn on a box and the routing pros will exchange information, and then the supervisor module will push a routing decision down into a line card. It works exactly that same way, so there's no additional latency.
How much of intelligence is taken from the hypervisors, assuming that I have a fully virtualized environment connected to the leaf? Is there any intelligence taken from the hypervisors to your controller?
So when you say hypervisor, do you mean hypervisor switch?
No, the operating systems, like take VMware or any other hypervisors.
So I apologize, that question doesn't make sense to me. So the controller is just a user space process running in an operating system, and it's talking to other user space processes over the network, which are the individual OpenFlow agents. There's no hypervisor necessarily involved in that.
So do you not allow even max learning in just the regular switching domain?
It depends on the application. Some yes, some no. And so MAC learning comes down to, so put it this way, MAC learning in the fabric doesn't happen because you're actually forwarding based on something that's not even MAC address. Or in the monitoring fabric. In the production fabric, the answer is yes.
What is the flow of the learn MAC address? Do you have to go all the way up to the controller, or is it just up at the agent?
No, it's just in the chip. It stays in that chip. I mean, it works exactly the way that it does with standard switching right now. So the controller pushes policy down onto the switch, and the time the packet shows up, unless it's the first packet or it hasn't been the first packet that has ever come from that box, then it doesn't go up to the switch, the controller. So go to the side of the house.
So you mentioned about customers with a depth, right? User request to get. I mean, if they have a bunch of switches and I have span for where does the value of system, I mean, does it go, all the data that offloads goes into the controller?
No. So the question is, we'll say, independent of that specific customer, how does all the data come from the production network into the big switch network, and so into the tap network? And so the idea is we actually program the chips to drop almost all the traffic and only forward the traffic that the operator is interested in. So you imagine a typical use case would be an operator gets a trouble ticket, server A can't talk to server B. And so 100% of the traffic from the production network is being dumped into our tap network. And then, say at startup, then 100% of that traffic is dropped on the floor. And when the operator gets this trouble ticket, he logs into our GUI and says, I would like to see the traffic between server A and server B. Please forward it to this monitoring station where I have Wireshark running. And then only that very, very small subset of the traffic will actually be forwarded. So we're actually using these chips as extremely high-speed filters. Does that make sense?
So the switches, they should be OpenFlow capable?
So the switches have to be running our SwitchLight software. It's even a stronger requirement than that. Okay. So it is a bare metal switch with our SwitchLight software on top of it.
Even if they need to just span with 1 or 2 ports, then also they have to run all of this at 48 port filters on them?
Yes. So I mean, frankly speaking, if they only want to span 1 or 2 ports, this is not a great solution. If you want to span hundreds of ports, this is the right solution for you, and probably the only solution, because yes, there are other monitoring products out there, but they generally don't scale up to that either in terms of the architecture or the price. Go to this side of the room.
So how far can you go back for history capture?
How far to go back for history capture? I don't understand the question. What's the context? There's no history.
Whatever that capture, you can also...
Oh, so let me explain more clearly. So what the Big Tap monitoring product does is live forwards packets from the production network to a tool like a packet capture device. So we actually don't produce the packet capture device. We just connect the two. And so it's up to the tool how long it's going to push that back. And I can't speak to other people's products very well.
So are you compromising on the feature side by restricting to a particular hardware? You can do more interesting things if you are virtual.
So the question is, are we compromising on a feature set by restricting to specific hardware? So exactly back to the original picture with the 4 levels of open versus speed, there's a very clear trade-off here. And so with the extremely fast ASICs that we deal with, we're getting a huge speeds and feeds. We're only able to replicate 90 to 95% of the features on a given chip of, like, say, some of the more traditional packet brokers. But to be able to do 10 times as much for the same cost and 90% of the features, that seems to be a reasonable sweet spot. Now, the features that we can't do with some of the ASICs, but we can do with others. So there's no one ASIC that does everything. And so this question is, which is the best one? So the ASICs we use, they do tunneling, they can do tagging, they do the filtering at line rate. There are other ones that do timestamping. There are other ones that do some level of packet deduplication. There's no one chip at these speeds that does everything for everyone. But being able to hit 90 or 95% of the use cases turns out to be okay.
For troubleshooting traffic issues on packet drop, there's a big tap. Is that the only troubleshooting mechanism or any other?
Not at all. We have lots and lots of very fun troubleshooting stuff. In the interest of time, I will point you to our network field day of last year video that we did. We did a full demo of that. Okay. One more for the side of the room, sir.
You frequently hear SDN with the network virtualization. So what is your opinion on this?
So when you say network virtualization, do you mean data center with lots of VMs, or do you mean network function virtualization? You could mean either of those.
Either one.
So let me take network function virtualization. A couple of us were chatting about this beforehand. In my mind, network function virtualization is taking a packet processing feature, so that's a firewall or a load balancer or something like that, and logically chopping that up and spreading that across, say, a bunch of VMs or something like that. So turning something that was a dedicated hardware appliance into a number of VMs. So in order to do that, your network has to be smart enough to spray the traffic across those VMs. And if those VMs move, you need to be able to update to where that's going. And if one dies, you need to stop sending that and rebalance that. So
SDN would be the requirement.
SDN would be the requirement for that. And so I think they're actually very compatible that way. And one may even say required, because there's some functions, to the question here, that these fast ASICs can't do, but if you have a lot of VMs that could emulate that, you can actually balance this back and forth. So I think they're actually very compatible that way.
So do you see any change in like applications from the SDN perspective for routing and switching, or we continue to use the same protocols?
I didn't hear all of your question. Do I see any changes in the what applications?
Routing and switching, the BGPs and OSPFs. Do we see a change in
So
with SDN? Do we see a shift of?
So it will absolutely be the case that as hard as I try, SDN will not take over the world tomorrow, and that those are the required protocols for communicating with the rest of the network. I think we're getting non-subtle hints. Let me just answer this question, and then I'll thank you guys. But absolutely, in the future, our controller will be speaking these routing protocols to communicate with the rest of the world. There's an interesting academic question of, 15 years from now, 20 years from now, when SDN has taken over the world, will we still use routing protocols like this? And that'll be interesting. My claim is that we will have routing protocols that look a lot like that, but SDN will allow us to evolve them faster because much as we claim to know and love BGP, anybody who's actually administered it thinks it's horrible, and we can definitely do better. And on that note, guys, thank you very much for coming. Thanks for even staying longer. All right. Bye.